Okay, in this video we're going to talk more about solving second-order linear homogeneous differential equations with constant coefficients. And we started off the last video, if you watched it, just kind of summarizing what the solutions can look like. So first you have to know what the differential equation should look like, and it should look like a y double prime plus b y prime plus cy equals 0. So the 0 is really important. That's what makes it homogeneous. That's what makes all these solutions apply. A, B, and C need to be constant. And as soon as you've met that form, what you really want to do is you want to find something called the characteristic equation, which is basically a quadratic that has A, B, and C from the differential equation as its coefficients. So we usually write it as A r squared plus B r plus C set equal to 0. So the differential equation is associated with the characteristic equation, and then the roots of the characteristic equation tell you basically what to write for the solution to the differential equation. So we already covered b squared minus 4ac greater than 0. We did a bunch of examples. It'd be useful, if you haven't watched it, for you to watch that video. In this video, we're really going to be concerned with b squared minus 4ac equals 0. So in that case, the quadratic itself has one real root. It's a double root, so if you think back to algebra 2, that means the quadratic kind of bounces when it hits the horizontal axis. And in this case, our solution is a little different. It looks almost exactly the same, but you really got to pay attention. It's y equals c1 e to the rx, that's exactly the same, plus c2, and then there's this factor of x that we multiply in, times e to the rx. So it's e to the rx both times, c1 e to the rx plus c2x e to the rx. I call that the rule of multiplying in an x. It probably has a better name than that, but I'm not really familiar with it. And so that's what will happen when we get one repeated root. We could also get our discriminant, b squared minus 4ac, could be less than 0. In that case, some other stuff happens, but it's not going to happen in this video. So we're really just focused on really the first two types, but really the second type, so where we get one repeated root. So I've always found it a little surprising that works, that you just multiply in an x. So I think a good place to start here on this type of thing is maybe like verifying a solution. So I already solved this differential equation, and I got my solution is c1 e to the 5x plus c2 x e to the 5x. We want to verify that that's a solution to y double prime minus 10y prime plus 25y equals 0. So one thing we could do, if we totally believe it, is we could just solve the differential equation, right? Find the characteristic equation, find the roots, and then just plug into that general form that we just talked about. But what I'm going to do is kind of go the other way. I'm going to take y, I'm going to find y prime, y double prime, and I'm going to plug into that differential equation, simplify everything, and show that you just get 0. So let's do that. I think it's useful to rewrite y first, so I'm going to actually factor out e to the 5x. So I get e to the 5x, c1 plus c2x. And now I'm going to find the derivative, which involves using the product rule, because it's a product. So first, derivative of the second, plus second, derivative of the first. And now we want to kind of simplify this. You can take out an e to the 5x from everything. So e to the 5x quantity, c2 plus 5c1 plus 5c2x. And that's y prime. So I'm going to write equals y prime again because I'm going to substitute and I want to be able to make it clear what's happening. We want the derivative of this, so that's the quotient rule again. First, derivative of the second plus second, which is really annoying to write, and then derivative of the first. And this also factors. You can take out an e to the 5x again. So we get e to the 5x, 25c2x plus 25c1 plus 10c2. Okay, so these are my values of y, y prime, y double prime. So let's box those. And what we're going to do is we're going to take those and just substitute them into the differential equation. So we're going to substitute right in there. Okay, so this is going to go, I'm replacing y double prime with what I got for y double prime. So we have this, and now I'm replacing y prime with what we got for y prime. And now I'm going to replace y with what we got for y. And then when I simplify all of this, I should end up getting 0. So it turns out you can actually take e to the 5x out of everything. Everything has a factor of that. And then for y double prime, there's nothing left to do. For y prime, I need to distribute the negative 10 to everything in there. And for y, I need to distribute the 25 into everything there. So I'm going to take out e to the 5x. I'm going to do all my distributions. So nothing happened for y double prime. Negative 10 gets distributed for y prime. And then positive 25 gets distributed for y. All right, now we look at this thing. And let's start with the c2x terms. Right, e to the 5x is fine. It's just going to hang out. So the c2x terms, we got 25, we got negative 50, and 25. But 25 plus 25 is 50, so we have 50 c2x minus 50 c2x. It's gone. Let's do the c1 terms. So 25 c1 minus 50 c1 plus 25 c1. Turns out that's gone. 10 c2 minus 10 c2. Turns out that's gone. So this really is e to the 5x times 0. So it's actually just 0, and we're done. All right, so the solution actually works, which I think is the first stumbling block you really need to get over. Once you get past that, let's solve some differential equations. So these are second order, linear, homogeneous differential equations. And we want to solve y double prime minus 4y prime plus 4y equals 0. Okay, it fits the form. It equals 0. We got y double prime, y. We got constant coefficients. Let's write the characteristic equation, which in this case is going to be r squared minus 4r and plus 4 equals 0. I look at that and I think I can definitely factor that. So that's going to factor into the quantity r minus 2 squared. That should equal 0, which means that really r just equals 2. If r equals 2, there's only one root. It's actually a double root, right? Because r minus 2 squared has multiplicity of 2, kind of from algebra 2-ish. So we have one double root. I know if there's a double root, the solution looks like y equals c1 e to the rx plus c2 x e to the rx. It's really important to remember that x. That's the thing you're probably going to forget. So I can write, in this particular case, my general solution is y equals c1 e to the 2x plus c2 x e to the 2x. And we're done. Let's take a look at another example. So let's say we want to solve 25y double prime minus 30y prime plus 9y equals 0. All right, it fits the form. We got constant coefficients. We got y double prime, y, and it equals 0, so it's homogeneous. So we're going to form our characteristic equation. So ideally, these become boring to you at some point. So we get 25r squared. Turns out the process of solving these is very much involved in the process of solving non-homogeneous linear differential, second order linear differential equations. Basically when they're not equal to 0, when they're equal to some function. So we really need to get good at this so that we can also get good at that. All right, we got our characteristic. I know how to factor this. So it's going to be the quantity 5r minus 3 squared. You can actually, if you needed to, you could use the quadratic formula on that. It would be totally fine. Whatever method you prefer, you could complete the square. I think it'd be crazy to do it on this, but you could do it. A lot of options for you. Let's solve. So we get r is 3/5. So that's a single real root. So I know exactly how to write the solution. So my solution is going to look like, it's always hard to put a fraction in the exponent. So it's c1 e to the 3/5 x plus c2 x, which we're not going to forget, times e to the 3/5 x. And we're done. All right, I'm going to do one more example in this one. So we want to solve 2y double prime minus 2y prime minus 7y equals 0. It fits the form. It equals 0. Constant coefficients. We see y double prime, and y. You could actually be missing y prime or y, and it would still fit. You cannot be missing y double prime, because it wouldn't be second order in that case. All right, so let's make a characteristic equation out of this. So we get 2r squared minus 2r minus 7. That's got to equal 0. I look at that and I think, I'm not really sure how to factor that. So when I'm not sure how to factor, I just immediately jump to the quadratic formula because it's going to save me time rather than just messing around. So opposite of b plus or minus square root of b squared minus 4ac. So a is 2, c is negative 7. So all over 2a. And then that's going to simplify to plus or minus radical 60 over 4. That's going to simplify to, so radical 60 is radical 4 times 15, radical 4 is 2, so 2 root 15 all over 4. And it looks like I'm actually not getting a double root here. I'm getting that R1 is 1/2 plus root 15 over 2, and R2 is 1/2 minus root 15 over 2. So this is not the same scenario, but that's okay because we already know how to solve this. We have two distinct real roots, so we can actually just write down our solution. So the solution in this case is going to be y equals c1 e to the r1 times x plus c2 e to the r2 times x. Make sure you put r1 and r2 in parentheses for this one because you need to distribute the x if you're going to keep going. All right, that's it. You got to kind of be on your toes now because you know two different ways to do it. I hope you found this helpful, and good luck.